The questions we're asked in the next two examples are identical to the previous two examples, but what will be different in these cases is that the second derivative test will fail, meaning we'll have to rely on the first derivative test to classify our points. And we'll see how that plays out. First, we need to find the first derivative of our function s of x. To do this, we'll require an application of the chain rule. So this will become 3 times negative 5x minus 1, that quantity squared, times the derivative of that interior function, plus the derivative of 3 will just be 0. So we'll get, that should be the derivative. So this will be 3 times negative 5x minus 1 squared times the derivative of negative 5x minus 1 will be negative 5, giving us negative 15 times negative 5x minus 1, that quantity squared. In order to find critical values, we still take that derivative function and set it equal to 0. In this case, all we need to do is look at solving negative 5x minus 1 is equal to 0, which will give us x is equal to negative 1/5. This means we have a single critical value. We'll try to apply the second derivative test, meaning we'll first find s double prime of x, which will give us negative 15 times 2 times negative 5x minus 1, now raised to the first power. Then multiply that by the derivative of negative 5x minus 1, which will just be negative 5, which will give us positive 150 times negative 5x minus 1. We have a single critical value, so we'll test s double prime evaluated at negative 1/5. Which will be 150 times positive 1 minus 1, which will be 0 times 150, or 0. Anytime the second derivative evaluated at one of those critical values gives us 0, we have an inflection point, so that's where concavity changes, and this test fails. That doesn't mean the problem is done, it just means that we can't use the second derivative to classify our points. What we have to do is go back to a sign chart for the first derivative function, plot our critical value, which is where our derivative function is equal to 0, and then choose test points on either side of that value. In this case, we'll choose negative 1 and 0. We'll look at s double prime of negative 1. Plugging that in will give us negative 15 times 5 minus 1 squared. That result will end up being less than 0. So everywhere in this interval, for all values of x less than negative 1/5, the derivative function will be negative. And if we evaluate the second derivative function at 0 as our second test point, we'll get negative 15 times 0 minus 1 squared. That result will also be negative. So for all values of x greater than negative 1/5, first derivative function will still be negative, meaning that our function is doing something like this, where it's decreasing, levels out or goes horizontal for just an instant at negative 1/5, and then continues decreasing. Since the sign of the first derivative doesn't change, that tells us that x equals negative 1/5 is neither a maximum or a minimum. The function never changes direction, it just continues decreasing, so we have no local maximums or minimums. Oh, I left out a word there. So it's neither a max or a minimum. We'll look at one more example where the second derivative test fails, but we'll move through it a little bit faster. We would need to apply the chain rule again, but we would find the first derivative of this function to be negative 8/3, x plus 2 to the 5/3. Setting that equal to 0 means we would need to solve x plus 2 is equal to 0, so we get x is equal to negative 2. We would find the second derivative of this function by applying the chain rule again, and we would get negative 40/3 times x plus 2 to the 2/3. And then we would evaluate t double prime of negative 2, which we can see inside those parentheses we would get negative 2 plus 2. So we would get 0 times negative 40/3, or just 0. What that means again is that the second derivative test fails. We're not done with the problem, but we need to do something else to investigate this point and classify it. That alternative approach is to look at the first derivative. We construct a sign chart, and we plot our 0 at x equals negative 2, and then choose points on either side of that as test points to plug into our function. We'll evaluate f prime at negative 3. That result will end up being positive. Again, all we're doing is plugging negative 3 into the first derivative function, and then we'll plug 0 into the first derivative function, and that will end up giving us a negative result. And what we see is that our function is increasing up to x equals negative 2, and then changing to decreasing, meaning that we have a local maximum at x equals negative 2. If the second derivative test fails, we can continue to investigate using the first derivative and constructing a sign chart.